what you have in front of you is a model for the gases, and it consists of small spheres that are called BBs, and those spheres are all identical, just like gas molecules are, and they serve as a model for what it is that we're trying to understand. And what I do in the demonstration is show a balloon, and I show 3 different ways to blow a balloon up. One is the usual way, by adding gas molecules. And that's the subject of the first part of the interaction, where I introduce you to the gas model. Okay? And what the gas model is a model of a balloon. The hard case is the Petri dish. That's what this is called, a Petri dish. And the BBs inside act as the air that is inside the Petri dish. And what we're going to do is look at things that we can't look at normally. We can't look at air molecules unless you have special equipment. So we make a model of that, which is this. And we look at this, and we try to force this to be as realistic as possible. And in the forcing of that to be as realistic as possible, we gain understanding as to how a balloon blows up. We're not interested in, everybody knows a balloon blows up. But what we're going to do is we're going to try to understand why the balloon blows up. Okay, so this is the balloon, and this is what we're trying to model. The model is in front of you, and what we're going to do is simulate air molecules interacting with a balloon by looking at the Petri dish. And the Petri dish is a confined space in which the gas molecules vibrate. Now, of course, you can see by looking at that the BBs, or the spheres, are not vibrating. So we have to supply the vibration. That's the artificial part of what we're doing. There are different ways to do that, and we are going to try to shake this in a random fashion so that the BBs interact randomly and they act like air molecules. Then we can see how air molecules work, and we can understand what they do. Why does the balloon get bigger? That's what we're trying to understand. Why does it get bigger? And so the first part of that is introducing the model. And we're going to do that now. We're going to film you guys interacting, and what we're trying to understand here is why the BBs act the way they do and how they interact with the sides of that. So if you guys want to just do that for a few minutes, shake it around, and then we're going to do some variations on that. And he's going to, Matt is going to interact, is going to photograph you doing this. So keep it on the table, keep it flat on the table, and shake it in a random fashion. Okay, random is not harmonic. Okay, that's a harmonic thing. Notice that all the BBs are staying in the center. What you want are them to act like gas molecules. So you want them to move all around in a random fashion. Do it. And watch them as they go. And you can talk among yourselves if you want to. Okay, whenever they clump together and they form on one side, that's not random. Okay, you want them to be hitting all the sides pretty randomly, and you want to look at them to see what they're doing in that process. You should notice that mostly the BBs hit each other. That's what you should notice. Mostly the BBs hit each other. But they also hit the sides, and when they hit the sides, they impart a force. Okay. All right, now what we're going to do is I want you to try to add some more BBs to that. Lift the tops off, okay? And I'm going to put some more BBs in. You want to see, probably show me adding more BBs to their thing. Okay, here. We're going to add a few more BBs, and then you should be able to tell when I do that, that there's going to be more BBs hitting the sides. Okay. There's going to be more BBs hitting the sides, and they're going to hit more frequently, although they'll probably hit, if you shake them the same way, they'll probably hit at the same speeds, but you'll just have more of them, okay? Okay, now put the tops back on and give them another shake. Now it's difficult to tell that more are hitting, but I think you can qualitatively see that more are hitting. And that's why, okay, that's why when I add more air to the balloon, there's more force on the sides, and that more force causes the balloon to expand, because when you have a greater force on rubber, it expands. Make sense? Okay. Okay, if we have time later, I'm going to add liquid nitrogen to this, and we're going to put a balloon in there and blow it up. But part of it is by changing the way that we shake it. Temperature is caused, when things get cold, they slow down, and they go very slowly. The molecules move slowly. And when they go slowly, actually what I want to do is take some of the BBs out so that we can see this a little bit more clearly. So I'm going to pour some of these guys out. All right, just a few. Let me do it so that way they end up in this. Okay, that's a good number. And when they go more slowly, of course, how often do they hit the sides? Less frequently. And they hit the sides less frequently and with slower velocity. And when they do that, the force against the side on the average is reduced. And when the force on the side is reduced, that means that the balloon can relax, and it causes the rubber to contract. Therefore, the balloon gets smaller at lower temperatures, and when the temperature increases, that means that the BBs go faster and they can hit the sides more vigorously. Could put the tops on. They can hit the sides more vigorously and more often because they're moving faster. So we'll do the slow one first. Okay, so just do it very slowly, randomly though, randomly and slowly. Okay. Okay. That's better. That's better. Randomly and slowly. Okay. It's really hard to do things randomly. Okay, that's low temperature. Low temperature gas. Now we want to do a high temperature gas. That means things are booking very, very quickly. So we do it very fast. Okay, so do it fast. Okay, you have to be able to see the BBs though, so very fast. Okay, slow. Do it slow. And do it fast. And do a trend. Okay, got to keep them in. The second way, okay, we're going to use the same model to simulate a liquid. Now what happens with a liquid? With a liquid, things slow down enough so that the particles can begin to interact. They can begin to stick together. If you know anything about water and steam, you know that water is a polar molecule, and polar molecules have electric fields that cause them to attract different parts of the other water molecules. So they start, when they're really hot, they just bam, and they knock off each other, and those forces don't mean anything. But when they get slower, they start to take effect, and they start sticking together. So what we're going to simulate sticking together with our model by tipping it up just a little bit. We're going to go from this position level to this position. And you notice that the molecules, the BBs, under gravity form a semicircle, almost like a meniscus in a liquid at the bottom. And so we're going to tip it, keep one part on the tip, and shake it back and forth, because they're still moving, but they're not moving quite as randomly anymore. Okay, shake it a little bit. Okay, keep them all on the bottom here, like that. Okay, and shake it back and forth. Shake it randomly on the table. Keep one edge on the table. No, back and forth like this. Like that. Just shake it back and forth like that. And what you should see is what happens in a real liquid. You should see that not all of the BBs are the same energy. Some have more energy, some have less. And they bounce around. And every once in a while, a BB gets enough energy so that it pops up above all the rest. It pops up above all the rest. Can you see it? Can you see it? Yes. All right, that happens. And what that is, you're simulating evaporation. That's what you're simulating. The molecules don't all have the same energy. Some have more. And when the ones that have the most can break through the surface, and they evaporate and go into the air. Now, because we have gravity here, they fall back down and come back inside. But that's the difference between reality and the model. Okay? In reality, gravity doesn't affect the motion of the molecules that much. But here, we're using it to simulate the liquid. So this simulates the liquid. All right, do it again. And make sure you have the liquid down pat. Okay? Something like this. Okay? Okay, can you see those molecules moving out? Okay. Good. You got a good one. That's a good one. That's a good one. You got a good one there. All right, and I'll show you some boiling liquid later on when we're talking about it. All right, that's the fourth one. All right, now the fifth one is the solids portion. And for that, what I think I would like you to do is to gather around, because I only have one thing. Let me explain it first. This is our simulation for a solid. Now, what happens when the liquids slow down so slow that they're able to kind of hang around each other a long time, and they come together and they get stuck in a position. Now, this is a good model. We're still using BBs. We're still using the spheres. And what we're doing is we want to have uniform attraction for each other. And how do we simulate that? We use a curved bowl. The bowl is curved, and if every BB was free to move, it would move to the center, right? It would move to the center on this. Well, all of them are trying to get to the center, so all of them are attracted to each other. Are they really attracted to each other like electromagnetic forces? No. We're using gravity again to simulate the slight attraction. But you'll see the amazing result. So come on up over here around this table. If you look, you'll notice that they look like it's a patchwork of crystals that form on the top. Next time you're in a hardware store, look for something that's galvanized, and you'll see this. And what's happening is, as the thing cools, the crystals form on the surface, and they form by slowing down. And notice, do you see any patterns here? Not too much, huh? But watch what happens. All I'm going to do, I'm not going to take each one and place them in a pattern. All I'm going to do is shake it and let nature take its work. And what's going to happen happens because each of these are trying to get as close as they possibly can to each other. That's what's happening. Here we go. Ready? It forms a crystal. Notice that every BB that's on the interior is surrounded by exactly 6 other BBs. Take a look. Everyone is surrounded by exactly 6.
Yeah.
You wouldn't think that you could do that just by shaking it a little bit. But what you're doing is you're shaking it and you're forcing an order because all the BBs are the same size and all the BBs are attracted by about the same force. And so they try to pack as close as they can to each other. And they form, this is called hexagonal close pack structure. Okay, and you can also form some other things. Okay, there you kind of mess it up, and then you just shake it like this. Okay, it took a little longer there. There were some slip planes that were in there, planes that didn't quite match up, and once they start to form and they can't match up, they sometimes remain permanent. Now I'm going to try to form a void in here. See if I can form a void. Almost. Hard to form a void.
You did this one.
I had to.
It worked the first time.
Maybe they're getting too slippery. Ah, there we go. There's a void. And a void is stable. Okay? It can form, and it's got 6 around it, but the center one is missing. But even though the center one is missing, it's stable. And it forms. That's how they make steel hard. They take hot steel, and when you do hot steel, those atoms are popping out all over the place, and they form a whole bunch of voids. Then you take the steel and you quench it in water, and you freeze those voids in place, and that makes the steel less bendable, so it's harder, and it can sharpen it faster. It's called quenching, and it makes the material less ductile. You know, like some things you can bend easily. Some things you can't bend easily. Steel, quenched steel, is very hard to bend. It breaks. It'll break like a crystal. Other steels will bend like a ruler will bend. And so this is a solid. It forms like that. We talked about the pressure difference in the model. The model produces a pressure difference, and one of the things that I do in my demonstration, if you remember, is I want to blow this balloon up, okay? And how could you blow this balloon up, knowing what you know now? Yeah, you know already, but those that haven't seen the demo, how would you blow this balloon up?
Maybe some sort of gas.
Well, there's gas on the inside, and that's pushing out. And we have also gas on the outside. Which way is the gas on the outside pushing?
It's pushing
In.
It's pushing in.
It's pushing in. Gas on the outside is pushing in. Gas on the inside is pushing out. So what we're going to do is take away the gas on the outside. Okay? And we're going to do that using this, which is right here. We'll use this, which is just a platform that has a hole in it, and the hole sucks the air out as long as you have something to suck it out with, and that something is a vacuum pump. So we're going to use the vacuum pump here to suck the air out from this enclosure, but the molecules inside the balloon, are they going to be sucked out? No, they're not going to be sucked out, but the gas molecules that are hitting the outside of the balloon are going to go away. And when they go away, they're not producing that punch. So the ones on the inside, their effect, the effect of the punch on the gas molecules on the inside is increased. And we attach it like this. You all know what a vacuum pump is? Pretty most? Okay. And you can see as the gas molecules are reduced, as they go away from the outside, the ones on the inside cause the expansion of the balloon. See, if you don't think about the model and what's going on, it's difficult to understand what's actually taking place. And every time I see this, I'm amazed, because you know what? Every time it happens. That's the difference. In science, it happens all the time, every time. Every time. And so when you're done, you can turn it off, and now you should be able to start to predict things. Once you understand how things work, you should be able to predict how things are going to go. So you can say, well, I haven't done this experiment yet, unless you've seen it before. I'm going to turn this off, pull the hose out. What should happen? Yeah, but then you have the question, is it going to go fast, slow, in between? Are there going to be any other effects? Okay, that's always neat too. But see, this introduces, there's something there that we encountered that we hadn't planned on. Now, do you think if I did the same experiment that when I pulled the cord out, the balloon would follow the exact same path? No, it's not. It's not going to do the exact same path. Why? Okay, those are the kind of questions that come in. Whenever you do an experiment, you do an experiment under controlled conditions, but there are always parts that are not controlled. And those things bring in the most interesting results sometimes. And so you always do experiments more than once. Turn it back on. Same thing happened. And now you can watch for differences. Okay, is that expanding at the same rate it was before? Is it getting the same size that it was before? It didn't follow the exact same path. Why is that? Well, maybe there was some chaos that was introduced. And what effects do chaos have on the system? We're being able to observe all those things and make statements about them because we're gaining information all the time. Every time you live, every day you go through, even though it says, oh God, this is the same meal I had last time. It's not exactly the same. There's going to be some difference. It was cooked longer or shorter, or maybe there's a burnt part. Something's different, and that different produces a different effect. Pretty much the same. You could characterize that as pretty much the same, but of course the path of the balloon is not exactly the same. Why? Okay, you may be able to answer those questions with better inquiry, better questions. All right, so that's the pressure type thing. And there's all kinds of implications and extensions you can make. The other part is the temperature, and I did bring some liquid nitrogen. And in case you haven't seen that before, I almost didn't get this. There was a long line at the proving ground. But this is this, and we're not going to get too close so that we're safe. But liquid nitrogen, you cool regular nitrogen well enough, and you get it to be very cold so that it starts sticking together and it forms a liquid. Now the energy that's being transferred to the liquid is causing it to jump out and boil. And we talked about boiling. We haven't talked all about boiling. Well, we have a lot of time left. And notice that when the temperature of the glass container gets about the same as the liquid nitrogen, it stops boiling as fast. And it's no longer taking as much energy from the glass. Now all the energy is just coming from thermal radiation. Notice the crystal structures growing on the outside. That's water vapor. Water vapor is forming little ice crystals on the outside. And those will continue to grow in six-sided things like snowflakes do because of the way that the solid is coming in. See, it's not forming the way we form that crystal. Now, the water vapor is hitting the outside and it hits it and loses all of its energy all at once and forms in the crystal. So it forms that crystal that grows longer and longer as more water vapor molecules join in that crystal strength, the crystal length. Okay, so that's what the liquid looks like. And that's what we're going to put a balloon. We're going to get a balloon here. I'm going to blow it up and tie it. Now you see what I do at the beginning before the students arrive. This is the backstage version. Okay. And I'm going to pour some liquid nitrogen in. Can't see very much. You can look down into it. Don't put your fingers near it or anything. And when it gets to be about the same temperature, it will stop boiling. Notice that the balloon kind of crinkled up, right? All right, and that's the gas molecules are slowing down inside that balloon. And so they don't hit the side as much. Also, you'll notice that you heard crinkling, okay? Rubber is crinkling. That means that it's changing. It was a solid before, but it was a flexible solid. Now it's not so flexible. Reach down inside. And now it's heating up. Ooh, I got this part. Now the energy is going back into the gas. It's speeding up, hitting those sides harder and harder, pushing the rubber out. That's temperature difference. We're not adding any gas. We're just making the gas that's in there higher energy, so it hits harder. Make sense?
Yeah.
Okay. You always have to ask that question. Did that make sense? And then you can put it in there, swish it around. And you can see it's all crinkled up again. All right, and we can take it back out again, and you'll see exactly the same thing. If I can get it. I think there. I just put it on the table there. If you do this often enough, and those that brittle crinkle that you hear causes some cracks to form, and sometimes it'll pop. Yeah, some of these doesn't quite uniformly heat. But the reason, oh yeah, there's a thin spot right there. The reason I can pick this up without fear of frostbite is because rubber does not conduct heat away very much. If this balloon was made out of metal, which conducts heat away very quickly, and I picked it up, you could get frostbite on your fingertips, but there's not really much chance now of it. Okay, so that's that. And then we talked about boiling, and I'll boil some water for you at room temperature. That was boiling. Okay, we still have a little bit left. Look at all the ice that's formed on the outside. And why can I hold the top there without fear of, would I hold the bottom?
Because all the liquid's down here and it's colder down here and it's hotter up here, so
Yeah.
it'll go out as vapor. And
Right, and how well does glass conduct electricity?
Not very well.
Not very well. Not electricity, heat. How well does gas conduct heat? Not very well, just like electricity. So I can do that without fear, too much fear. And then if I get some water here, let me get some water. I pour it in here. And again, we're going to use the information that we got from understanding about our model. Why is this not boiling? Why are not the molecules in here that are moving fast, why aren't they just popping right out? Are they? First of all, are they? Yeah, a little bit. And that's what evaporation is caused by. But why is this not boiling?
Because the atmospheric pressure is causing the water vapor the water to stay in a liquid form.
Right. We have gas on top, and that gas is pounding the top of the water. Any gas molecules that try to escape have a reduced chance because of the pounding. So what I'm going to do is take away those gas molecules with the vacuum pump. Then we'll see what happens. All right, our trusty old vacuum pump. I have to put the cork on the top so air doesn't replace the gas that's being taken away by the vacuum pump. And here we go. Now you'll see a couple things happen. So this is the added additional part. You'll see the air come out of the water. Air's gone, now it's boiling. You see bubbles forming because the energetic water vapor molecules that are in here are able to make their way out without opposition to any atmospheric gases on top. So they boil. This will boil away. And if we had a thermometer in there, it would actually notice that the energetic ones are leaving. So therefore, which way should the temperature go? Go up? Energetic ones are leaving. It's going to go down, right? It's going to go down. So now I'm going to turn it off again, and we repeat the experiment. You'll hear, you hear the thing go in. I'm going to repeat. Now we have no boiling taking place, but now you will not see the air leaving. Why?
Because all the air already left.
It's already left. You'll just see it start boiling. Okay, it just started boiling. So I'm going to shake it up, and air is in there. I'm going to shake it up. Listen, listen. Do you hear it? Okay, well, what happened was the air that was in there went into the water, and so there had to be more air to replace it. Okay, everything that you see or hear in terms of, all right, now we'll do it again, and let's see if we can see the air come out again. The air came out. Okay, you saw it come out, right? Now it's boiling again. And not only that, but you understand why it's boiling. And now you understand also things that you might have to extend this information to. Why is there no water on the surface of the moon?
There's no atmosphere.
There's no atmosphere, so there's no gas molecules hitting it to keep it there. And so what does it do? If there was water on the surface of the moon, it would do one of two things.
Cool into a solid form or evaporate.
Or boil away. There are no liquids in space. No liquids in space. That's why it's dangerous for people to go into space without a spacesuit. Is your blood a liquid? What would happen to your blood if it were exposed to a vacuum? It would boil. Okay, it would boil. Your eyeballs would pop out. All kinds of things would happen. And this is another form of the solid here. This is these are small spheres that are magnetized, and if you get the right number in the right order, they'll form a nice hexagonal structure, and you can pull these apart, okay, and put them back together again. They used to sell these at the Science Museum in downtown Baltimore, and for some reason you have a hard time getting these anymore. I think too many kids swallow them. And it's not a good thing to eat, to swallow these
I
things.
think they're putting them in their mouths and then putting one on the cheek and it would stay there.
Would it? Okay, I never did that. But yes, it would. It would do that. But these are more difficult to get now because of the liability. And that seems to be a bigger and bigger issue. As kids do stupider and stupider things, that's what happens. Okay, so don't do anything stupid, and you know a little bit more about solids, liquids, and gases, right? Okay. All right. Do you have any questions? Okay. Okay, I think we're just about done. That was good. Got it all done. Got it all done. Okay. I think that's about it for this. And we'll start packing up and heading out. Question?
What would happen if you put liquid nitrogen in that little beaker that you boiled the water in,
Oh, this one? Yeah.
and then you used the vacuum on it? What would happen?
Well, it would boil really fast. Okay, it would boil even a faster state than it was before, because the air is the temperature of the liquid nitrogen at atmospheric pressures is 77 Kelvin, which is you know the Kelvin scale? Okay, it's 77 Kelvin. It's pretty cold. About minus 200 Celsius. Okay, so that's really cold. But if you put a vacuum on it, the temperature drops to a lower temperature, maybe 70, something like that. No, it would be really cold. You would be so cold that you could start forming solid nitrogen, and that doesn't stay around very long. Solid nitrogen, but there's solid nitrogen. I think is there any solid nitrogen on Pluto? I don't know, but it gets really cold. You can look up the freezing point of nitrogen, and that's the temperature it would be. I don't know it off my head. Yeah, question?
I was going to say that it was formed solid nitrogen.
Yeah, it forms solid nitrogen, right? Right, yeah.
How would you know if there was a void in the crystals and something like the crystals on there?
Well, first of all, when the crystals form, anytime you get a mismatch and they stick together, you're going to get a void or some other defect in the crystal. In order to form perfect crystals like transistors, when they grow silicon for transistors, they try to form perfect crystals. They don't want any, and they have to grow them very slowly. They slowly evaporate the silicon onto a crystal substrate, a single crystal, and it grows into and you can get a single molecule that is this big, and then they slice it and they form planes, and they use lasers to make the crystals. But defects like voids, a void is a defect, form whenever you form crystals. You have to do it very. Oh, there you go. You got one. Okay, and you can get them all over the place. How slowly it grows and what the conditions are for it to grow. If you do it very slowly, so that no voids form, you can get it. But it takes a lot of work. Those are defects. And see, it would have lower energy if I took this crystal or this ball right here and put it in the center. The whole array would have a lower energy, right? This has higher energy than the array would have if it were a perfect one, but you have two things competing. You have energy, and does anybody know what the other thing is? You probably won't study it for another 5 years. It's called entropy. You've heard entropy? Entropy is the measurement of randomness. If you have all of these in a perfect order, what's the randomness? Very low. The randomness is low. And so you have a competition all the time between energy and entropy. And a natural state has a certain entropy and it has a certain energy. you can lower the energy, but you have to decrease the entropy in order to lower the energy as well. And that is a study of thermodynamics, which is another area of physics. How your refrigerator works and all that stuff is a combination of entropy and energy and transfer of energy. But everything has randomness to it. You just have to be to control it. You have to set the conditions so that you can get things to work the way you want them to. Okay, anything else? Okay, we got to be out of here at 4 o'clock. So we're going to start to break down now. So if you have a quick question, we can answer it. Are you trying to form one? There you go, you got one.
Like bigger void than you did.
Sometimes you can get, okay, you see that right there? That line is a slip plane right there. Notice that all the molecules are lined up here and all of them are lined up there. But right along there, they're mismatched, and that's a fault. That's a fault. And all you have to do is usually move it. That's a low energy fault. And you can see when you put your finger in, you're creating slip planes all along there. But they go away easily. They evaporate because they want to get to the lowest energy. There you go. Got it. Okay, thank you guys so much. We couldn't have done. You'll be immortal.